Hi, and welcome to Allen High School's discussion of electrochemistry at the AP/IB level. To start our discussion, I'm going to do this a little bit differently than many schools do, but I think it just makes so much more sense this way, so hopefully you will agree with me. Let's take a look at this reaction. I picked these rather randomly. This would be a net ionic for, say, a single replacement reaction. The very, probably the most simple and basic of redox reactions. Now, in redox reactions, there's an exchange of electrons. So really quick review of that. Now, this is not balanced yet. We want to take a look at that first. So let's start with balancing the very simplest of these reactions. Later on in the unit, we'll get to more challenging ones. Let's zero in on what happened to our lead. So I'm going to focus only on the lead, and somehow we keep neglecting this, forgetting it. Pure elements, all by themselves, not bonded to anything, have an oxidation number of 0. Now, let's take a look at what happened to the lead. It went from lead 0 to lead 2+. Now, because it became less negative, since we're talking about electrons, I like to discuss it in terms of less negative and more negative. Since it became less negative, it must have lost electrons. And indeed, it lost 2 electrons. So if it loses electrons, we're going to put them as a product. And loss of electrons is called oxidation. Now, this doesn't give us the full picture. This only gives us half of the picture. Therefore, we call this a half reaction. We can't have oxidation without reduction, so let's zero in on the chromium. Chromium went from chromium 3+ to chromium solid. I'm going to be very explicit. Chromium solid has an oxidation number of 0. Now, it became more negative. Just think of a number line, draw a number line if you have to. And I need 3 electrons. Notice that when I'm doing this, I am balancing charge right now. Really balancing electrons and charge. So, if you'll, and that's a good check that you've put your electrons on the correct side. 3 negatives, 3 positives equals 0. So I have the same charge on both sides. Now, this is a gain of electrons. Gains are considered reactants, so you would always put it as a reactant. And this is called reduction. Now, there's a couple of ways to remember that. You're actually reducing the oxidation number, but a common way is to use the phrase oil rig. Oxidation is loss, reduction is gain. I'm not going to write that out because I believe you've seen that before. So oil rig, oxidation is loss, reduction is gain. Now, I can't lose in a system, I guess I shouldn't personalize it, but in a system, we can't lose 2 electrons and gain 3 electrons. Where's that other electron, emerging from? We don't create and destroy electrons. So we have to gain and lose the same number of electrons. The least common multiple of 2 and 3 is 6. So I'm going to multiply that half reaction by 3 and this half reaction by 2. So if I did that, my balanced reaction, overall reaction, would be 3 leads plus 2 chromium ions yields 3 lead 2+s plus 2 chromium solids. Now, you want to check that when we're balancing, we balance electrons, we balance charge, and we balance elements. Normal balancing focuses on these. In this unit, we want to include electrons and charge. Now, on this side, I have 6 positives, and on this side, I have 6 positives. So I have balanced my charge. Since it's a net ionic, that charge isn't 0, but it must still be balanced. Okay? So let's take a look at our summary chart, and then we're going to come back and continue this conversation and this study of this reaction. Our species that was being reduced was the chromium 3+ ion. Be very specific. Include the oxidation number. You want to make it very clear in your evidence when you're trying to argue your point or justify your point, that you know what you're talking about. If it's being reduced, something is happening to it. Therefore, it must be a reactant, not a product. Okay? The species being oxidized was the lead. Be specific. Say lead solid or lead 0. The lead atom. Somehow be very, very clear what you're doing. And again, it has to be a reactant. Something is happening to it. Our reduction half reaction was chromium 3+ plus 3 electrons yielded chromium solid. Our oxidation was the lead 2+ ion yielding lead plus 2 electrons. Okay, now that's all we can do on this little summary chart here because I haven't talked about this part yet. So let's back up a little bit and have a quick discussion before we jump into our next video. I have electron exchange going on here. If I have electron exchange or electron movement, I have the potential of doing work, having a current flow. So that's what our question is. Is this spontaneous? In other words, can we count on there being no thermodynamic barriers to this proceeding to going product? If so, can I somehow capture those electrons to perform some useful work? Or is this non-spontaneous? Are there thermodynamic barriers that prevent it from going to form product? If so, am I going to require some sort of work in order for this to happen? Am I going to have to push my electrons because there's a barrier to their flow? Am I going to have to supply a source of power via a battery or a power supply? Those are the questions I'm asking of this reaction. Okay? Now, in order for that to happen, I somehow have to separate them. Right now, the electrons are going directly from one substance to another substance. Is there a way for me to separate these half reactions in order to answer these questions? Well, that's what we're going to address in our next video. So until then, this is signing off.